if you're aligning all the electron spins or the nucleon spins, the metal is not going to behave structurally the way it would normally behave. I mean, just think about it. If you take all the electrons or nucleons in your body and you align them, your body's not functioning the same way.
That's a very good. I haven't thought of that.
You know, I mean, in an MRI, they, it's not, so it involves the spin of hydrogen. It doesn't involve the conduction of electricity in your body, and it doesn't affect the binding of the cells or the chemicals. But what you're talking about is I don't think inertial mass can be reduced, because the fields that are contained in matter contribute to the inertial mass. So if you go in and you try to muck around and make all the spins the same, the fields that require that are going to need to be maintained in the material, and so the inertial mass, if anything, will get heavier. The fields contain energy and they contribute to the mass. The only way you can reduce inertial mass is you have to release binding energy. So when two atoms or molecules come together and they bind, binding energy is released as photons, and photons don't have gravitational mass, and so the inertial mass is what's reduced. And I personally think it would be, if you're doing experiments that are focused on or hypothesized to reduce inertial mass, I don't think they're going to work, just as a matter of energy conservation. I think that the effect is much more like what Richard explains, where there's a relativistic electric effect, and you're creating thrust. So here's the thing: there's two types of propulsion. There's a pulling propulsion, and there's a pushing propulsion, right? And so the only thing that we know that pulls is gravity, and everything else pushes. And all these propulsion devices are pushing. But none of them are changing the inertial mass. In a warp drive, that would be a pull drive, right? Because you're compressing space and you're pulling your craft into the space in front of you. So I think inertial propulsion has to do with those concepts and not inertial mass reduction. And when you see craft change direction very, very quickly or zip away, what's happening is that the clock on the clock rate, they're actually modifying it and speeding it up. And so aboard the craft, they're experiencing a right angle turn over the course of 10 seconds, where you might see it happen in 1 second, because their proper clock's been decoupled from the coordinate clock, or the coordinate time. Their proper time's decoupled from the coordinate time, and so they experience the turn, let's say, over 10 seconds, based on their clock rate differential. And you might look at it and see it happen in 1 second. So they have control of the clock rate, and they also have control of the rule of measure. And so they can actually adjust the distance that they want to travel. So you and I want to drive a mile, we have to drive a mile, but they can actually adjust the rule of measure and make their measuring stick larger, so that they have a 10 meter measuring stick, or a 10 kilometer measuring stick. So instead of the distance being 10 kilometers for us, it's only 1 kilometer for them. I think that's how they're doing it.
I'm sorry. I just want to jump in really quick. Also, this is something I've talked about this with Dennis Bushnell over at NASA several times. I would say, all things being equal, he's a favor of robotic intelligence over human intelligence for any kind of exploration. And that goes back to the Mars probes. That's kind of the beginning of it. But the idea is, UAPs, if we're talking about some kind of an extraterrestrial craft, odds are whatever's inside of them is a machine, you know, or it may be just the craft itself. There's no guarantee that there's anything biological in them that would get hurt by sudden acceleration.
Oh, but I mean the just the structure of the craft will just, you know, disintegrate. You don't have to have it manned.
Well, it's a good point. It's a good point, but
I think what Eric,
so there is something going on. There is something going on to protect the integrity of the material of the craft, even if there's no occupants.
I think what Eric's trying to talk about is warp drive, and the concept of warp drive has been promulgated in this field extensively. In fact, if you do any research, simple Google search, you'll find the Alcubierre drive and all these concepts, and they're pretty much a dead end. And this area of science being the holy grail of science, I would expect there to be a ton of disinformation, including Einstein's theory of warped space, which has never been proven. He has proven that light curves, or electromagnetic fields curve around gravitic, fields, but that doesn't prove that space itself is warped. There is one team that's working with 90-degree angled antennas.
Variable angle. They could be anything between 25 degrees and 90 degrees, according to David.
Right. Jeremiah actually spoke to him from Space Warp Dynamics. They changed their name. They're the only ones who are working on anything even remotely close to a concept of a warp drive. And I currently don't believe that warp drive is possible, mostly because there hasn't been any engineerable study of what can be done. There's no buy list from eBay of what to buy to build it.
Even though you and I, Mark, will disagree on this, and we're going to work together in partnership, I totally agree that warp drive is possible. So if you take a look at any material, whether it be optical or magnetic, you have something called a saturation limit, where you only have so much of this material that you can reorient or polarize, and you end up with a curve in terms of the response of that material versus an input flux and the time rate flow through it to change. So if you take, for example, ferrite, a ferrite transformer, common switch mode transformer that we have inside of every electronic device, right? If we add a greater field to that ferrite, it can only switch so many of its domains and polarize. So if we give more and more flux to it, it'll actually reach a point where it will no longer respond at all. And now all the magnetic fields that we put into it, all extra current, is now externally expelled from it because it doesn't have any more domains to flip. Now, we understand from the space-time curl vector with Maxwell's quaternions that you also have a saturation of the maximum density of energy that you can push through space. And so if you consider that you could create a high enough electric field potential over a short enough period of space where you have an incredible volts per meter, amps per meter, theoretically, you could modify the properties of space and change its saturation potential so that you have a parametric system where you have a response on a different axis. It's not coupled to the original input signal. So I guess my question.
That's what the scalar potential is doing. I mean, you're building up potential over time at coordinate positions, and that's one example of how it might be done. Hal Puthoff, thinks he can modify the metric, but the way he wants to do it is he wants to get a really high charge mass ratio going. So he's looking at physical charge, where I think he's wrong. What you're saying and what Richard's saying is it's much easier to do with voltage, right? So charge, charge represents a voltage in a way, but what Hal wants to do is he if you look at his metric in his papers, it's Q over M. And so he's looking for ways to get a high charge to mass ratio, but there's no way to do it. Even the sun, which is probably, other than an electron and a proton, the sun comes the closest because the sun is very positively charged because all of the negative electrons are ejected out of it. And even then, it's not gonna cause the metric to change very much. So, yeah, I mean, I agree with you, and but I also think it has a lot to do with time dilation. So, gravitational time dilation is proof of that, right? So things accelerate in the direction of increasing time dilation, and that's pretty much what I'll say about that is that gravity proves that time dilation does cause acceleration, and you can say that gravity is not a force, and it's actually a construct of the geodesics and the curvature that matter introduces into space. So, but I just want to leave you with that thought.
Well, so, and if it's okay, I may be paraphrasing, but it sounds like what you're saying is you would want to shoot to modify time more than modify space.
I think personally, my opinion, after years and years of thinking about it and reading, is that time dilation can be controlled. I mean, in gyroscopic experiments, it happens, and I was involved in a bunch of gyroscopic experiments, and we discovered that spinning disk dilates time, right? And so,
is there a requirement for a magnetic field, Eric, in that spinning disk experiment? Because this is something that Mark and I have discussed at length. Could you give more information about that particular example?
No, I can't, because it's not. It's an older project that I'm no longer involved with, and my NDA is expired. But a lot of people would get mad if I talked about it. I'm not precluded from talking about it, but it wasn't anything that was significant. We never got a whole lot of nothing ever lifted off the ground, even though it's possible. And I had some ideas on how to do it, but nobody else wanted to do it because it would have required a design change, a big design change. But the essence of it was that velocity functions in space. So if you have something orbiting the Earth, it has to travel at a certain velocity to stay in that orbit, right? And so that tangential velocity correlates to the time dilation of the gravitational field, pulling you down from that altitude, right? So the velocity that you have to travel to stay in orbit at a certain altitude is correlated exactly with the amount of time dilation that the gravitational field is exerting on you to pull you down into the Earth. And so the time dilation on the Earth is stronger than it is at higher altitudes. And so when you have a spinning disk, you're actually causing these latent time dilation gradients to form in space. And but the trick is to figure out how to so the secret is to figure out how fast you need to spin each disk, where the disks are located. So everyone thinks it's one gyroscope. There's more than one, and there's lever arms going on, and there's multiple gyroscopes for plane balance and stuff like that. And there's multiple ratios of how fast does this gyro have to spin, and does it have to spin on a horizontal axis or a vertical axis? And then does the whole mechanism have to rotate? Right.
Right.
I mean, look at Lathwell. His gyro did not quote unquote lose weight until he started to rotate it around his head, right? And so part of the gyroscopic mechanism is not just a spinning disc, but it's the rotation of about the central axis.
The precession.
Well, it's precession, but actually the most the biggest bang for your buck is orthogonal, right? 90 degree. You don't want any angle there. You want to have either
Yeah.
a 180 or a 90. That's why I want to give a talk on right angles. I told Tim, because I think propulsion basically comes down to right angles.
Yeah,
when you
last APEC conference, Eric, but we actually had a demonstration that was streamed in the last APEC conference of a gyroscopic device using 2 gyros that were rotating. If you would imagine 2 wheels, spinning free on their shaft, propped at the front of a car, that's what these gyros were doing, and they were precessed back and forth at 90 degrees. So they were on some servo control motors, and they started out at right angles to each other, and they moved forward to a sharper angle, and then moved back at a slower speed. And this device,
I know what you're saying, and they sort of try to like roll themselves forward, right? Like a rowing motion. The angle,
I guess you could look at it like that.
Yeah, that's not the right way to do it. There's a way to do it where you don't have to do that. You have continuous, even motion.
Continuous. Wow, that's amazing. I'd like to know about that.
It's not amazing because what you're doing is you're wanting to create a time dilation gradient across the object that you're accelerating. So everything accelerates in the direction of increasing time dilation, right? Gravitational field, you're pulled down to the Earth because the time dilation on the Earth is stronger than it is at altitude. So what you want to do is create a time dilation gradient across the ship or your body or the device such that the time dilation is greater at the front of the craft or the direction you want it to move than it is at the aft of the craft. And that's basically, that will cause propulsion in the absence of any kind of warp or compression of space.
Well, it would, but a time dilation is effectively a warp of space, is it not, Eric?
No, it's not. It isn't because a spinning disk, when a disk is tumbling over its over its ends, like if you have a cylinder, then that there's a torque there. But when you just have a wheel spinning, there's no distortion of space going on. There's just a wheel spinning, right? It's just rotational. In fact, in its frame of reference, it's not even spinning, right? You can have a rotational frame of reference. So, no, I don't think space is being warped by a spinning disk. I mean, maybe I'm wrong, but
I understand where you're coming from. I mean, I agree with the Lorentzian invariance and understanding how you can transform momentum in the way that Richard is doing and what you guys have been working on. That's, I think, the really the fundamental way that we should be going in terms of proving this stuff out.
Well, let me just clarify. I'm not talking about, what I'm talking about here is not related to what Richard's doing or field propulsion technologies. This is stuff that I worked on before that. Right, the gyroscopic stuff has nothing to do with Richard's stuff.
Yeah,
this is something that I worked on prior.
And if I could jump in, yeah, Jeremiah, and some of this is stuff Eric had discussed, maybe talking about this, but then he's under some NDAs also, and so he had some concerns about basically sharing too much, sharing some stuff that would upset folks. So that was in this case today. That was kind of why we thought, just supporting Richard's work, because he's collaborated on that too. So.
Yeah, I'm sorry. I don't mean to probe and try to get anybody to say something that they shouldn't be saying.
No. I just wanted to make a general point. I wanted to also clarify that what I'm saying with respect to time dilation is not what Richard and FPT are doing. The only comment I made was that I agreed with Mark, I think, about voltages being able to possibly warp space. Because if charge can warp space and mass can warp space, then why can't a voltage, right? So
right, what variable is it that's actually warping space when you apply a high potential between two given points at a certain distance apart?
Well, so mass is mass is a proxy for matter, right? So you don't need mass to accelerate. So charge, the only thing that really exists is charge, right? So in all the equations, charge and mass is interchangeable, right? So, and that's why you can't really modify inertial mass. So you either have to build up a large amount of charge, like is what Puthoff wants to do, like build up a huge amount of charge in a small volume with a small amount of mass, so that Q over M is very large, and that will cause the metric to change and space to warp. But I think that he's not looking at the fact that if you can just control the potentials, the voltages in space, that sort of correlates to the charge, and that you might be able to warp space using voltages rather than charge or mass.
In order to
I'm
see
sorry,
a
I'm
reasonable
really dehydrated here.
shift, I mean, how high would we have to be talking? 500,000 volts, 1 megavolt? I mean, are we talking significant volts per meter here? Just how strong will we have to have the differential over a given volume to really see anything?
I do not know the answer to that. Honestly, I don't know the answer.
Yeah, I'm sorry. That's a stupid question to really ask off the top of your head. But
no, it's a very good question. I mean, I don't think that anybody knows the answer to that, but it's obviously possible. I mean, these craft are zipping around, and but I do know it takes very little energy in a gyroscopic mechanism to make it to make a lot of things happen. Like we were only using like 250 watts, and we were getting rigs that were 300 pounds heavy to almost lift themselves off the ground. I mean, these things were trying their hardest to get off the ground, and they often flew off the table, right? And but see, the force vector was precessing, right? So we could never quite get the force, the thrust vector to point in the direction that we wanted the device to go. So it would always have like a washing machine effect. And but there were several times where the washing machine effect clearly was not there, and the device was going definitely in a direction, in the preferred direction, for more than just a millisecond. I mean, it was like, 1 or 2 seconds. But it's very hard, because just like Richard said, he wasn't working on this, but in order to rotate anything more than 5,000 RPM, it's very, very hard to do, no matter what kind of material you have. It just seems like 5,000 RPM is like sort of like one of the thresholds it's very hard to pass for any type of disk rotation. So
This does.
So anyway, go ahead.
This one does 10,000.
Well,
yeah, and my DVD-ROM here does
10,000, but that's also very small. I think if you're going to really do it, it needs to be a lot larger than that.
Okay.
Is there a reason, Eric, why it needs to be larger? I mean, is there an effect that we wouldn't see on a smaller scale that we should be looking for?
Yes, because it's the radius, it's the matter at, so you want all the mass to be at the
tip velocity, the edge velocity, the actual
you want as much mass as possible to be around the the edge. Circumference, right? But there's another term for it. You want the as much mass as possible as far away from the center as possible. That's one of the keys to it. Because what you want to do is you want to you want, yes, I mean that's the ideal, right? The ideal. And using something like iron is ideal because it's the heaviest element, right? In terms of density, I think, or what is it? Packing density.
Osmium is the heaviest.
Which one?
Osmium.
Okay. Well, iron's pretty close though.
Yeah, I know it's a careful balance between getting structural properties that are ideal and being able to maintain that high velocity. I mean, that's why
Well, I'll
carbon.
just tell you, it involves three different axes of coordinated rotation of spinning, and then the whole mechanism has to rotate. So wherever your gyros are, they can be spinning, but it's not going to do anything until the whole thing rotates like a helicopter blade. So you
if we
can
were to
imagine
take,
having gyros.
sorry, go
Go
ahead.
ahead.
I was asking, so you have a situation where you have what, 3 gyroscopes? Is that right? And each of them is on a different axis? Or no?
You can have as many. So you don't need gyroscopes as much as you need spinning discs, and I mean so in order to stabilize it, you would need 4 spinning discs, right? You want to stabilize it so that it can hover flat, and you don't want it to. Actually, you only need 3, but it's easier to do with 4. It's either the control system's easier to do with 4. And so you want to be able to spin at least 3, if not 4 discs, either parallel to or perpendicular to the Earth's surface. And then you want that entire mechanism of discs, which are all on lever arms, to then rotate around like a helicopter.
So if I were to understand this correctly, imagine you had a shaft in the gyroscope that, the gyroscope disc is 2 inches in diameter. Your shaft is 1 inch on each side. You take that shaft on one side and you basically mount that to a point and you tilt it 90 degrees to its axis. Then you would rotate that entire thing around effectively. Am I understanding the geometry correctly? I guess I can go on video.
So the lever arm. So take Lathweil's disc, right? The disc was spinning at the end of the rod, right? And he had it so that the disc was perpendicular to the Earth, right? Remember, when his arm was straight out, the disc was perpendicular. So just imagine that. What if instead of him being the one to spin that around his head, he just stuck another spinning disc on the other side?
So you have a disc like this. This would be a rotating surface, and then this would be your mounting point, and you would rotate this whole thing around basically like this.
Yes, but I would put another disc on the other side. So remember, Lathweit, if you looked at his video, he had one rod with one disc on the end, and that disc was spinning, and then he used his body to rotate it like a helicopter around above his head. Well, replace his body with just another disc spinning in the opposite direction, right?
And this ends up generating a non
and then rotate that like a helicopter, like he was. And I'm not saying that you'll see it lift, but I'm saying that that's part of the key.
Yeah, I mean that's what Sandy Kidd did, but he had a slight angle on those 2 gyroscopes.
That's not the way to do it. I know that experiment, and I know that he got that to displace itself, but and I've seen other gyroscopic experiments where people are spinning the disc and then they're raising it and then letting it fall and like swing like a pendulum. And as it does that, it will move the device forward every time the pendulum swings, because that effect is going. But you don't need that. You can have continuous motion without resorting to changing the angle. What really matters is the lever arm and the moment arm distance. So you have the center of the rod, then you have the 2 spinning discs on each end, and then each disc has the same diameter, and then the distance between the top of the disc down to the center of the rod, that's like the hypotenuse, right? That relates. So that distance, there's a formula that relates that distance to the angular velocity of each of the discs to the rotational velocity of the whole mechanism. And there's a formula that you can derive empirically through testing. And at some point, you'll notice something cool happen.
Wow.
Yeah.
That's very, very interesting,
It
Eric.
works. It works, but uh, it works, but you have to have it. You have to have it thrust at 9.8 newtons, right? If you're not if you're not getting the thrust, if you're not getting the thrust of gravity, it's not going to lift itself off the ground, right? So the other thing is, don't test it in the vertical mode, right? So don't try to get it to lift. Put it on a train track. And I'm not going to tell you the secret there, but you can imagine how you might have to change the orientation of the discs to make it go horizontally rather than vertically, right? But when you test it, don't, like, everybody tries to get things to lift off the ground. Try to get it to propel across the train track, because
Yeah, I was thinking about that. Why did Sandy Kidd try to use a vertical orientation instead of a torsion?
well, because he
pendulum?
just wasn't thinking, right? You don't want to fight gravity when you don't need to, right? All you want to do is you want to prove that the device can propel itself.
Right. That means that it
So-
produces a force that's independent of gravity. It's not a response to gravity or a negation
Right.
of gravity. It's actually an independent force entirely.
Right. People want to try to get anti-gravity, but that's not what you want. What you want is either a pulling or a pushing force.
Right.
You want to be able to propel yourself and push off of something without expelling mass. And the only way you can do that is by compressing space or by dilating time, right? Or by doing something like Richard's doing, or like the EM drive is doing, or like, doing something electromagnetically. So those are the three ways to do it, right? There's time dilation, there's space warping, and then there's electromagnetic effects.
If I can ask you one last question, Eric, just to define with a little bit more clarity, what is the primary difference in your view between time dilation and space warping? Because in relativity, they're kind of the same thing.
Well, they're not. I mean, time dilation is a function of the velocity, the velocity of the reference frame, right? There's nothing. There's length contraction. There's a difference between length contraction on a ruler and actually compressing space-time itself, so that the actual fabric of space is compressed. Length contraction only occurs on the object, on the matter that's traveling at a velocity.
You're talking about an external field that warps the entire volume of space instead of the response to the object itself or the point of charge. So
Well, there's right. So length contraction is a result of special relativity, and that is that's a contraction of the physical space, the entire physical body that's moving. But that's different from the type of contraction of space that you get from a massive body like the Earth, causing a curvature, right? And so that's not special relativity. That's general relativity. So there's they're separate things. You can dilate time through special relativity, which also results in length contraction. But you can also dilate time without length contraction, for instance, by using a gyroscopic mechanism, where what you do is you correlate the velocity, the orbital velocity at which a satellite has to orbit in order to stay in orbit, and balance out the gravitational pull downward, where the gravitational pull downward can be written in terms of the time dilation gradient from the object, that the gradient that's impressed upon the object by the Earth. Do you understand?
Sorry, it took me a minute to get my video back up online. Yeah, I understand. There is definitely a difference there between those two factors, where one is local and one is field. One affects things outside of the physical object itself, and the other one simply does not.
Right. I mean, I think like a warp system would be exterior to the object, and it would actually manipulate, space-time or the metric.
Right.
And then
the other one
there's,
is the object itself that only experiences this relativistic change.
right. I mean, the whole reference frame does, but even in your body's full of different reference frames, because everything in your body is moving at different velocities, right? So when it comes down to it, it's going to be an average over all of the different components that are moving. But the point that I think you might not be quite getting is that a time dilation gradient in space will cause acceleration. So if you had a clock 5 feet in front of you that was running slower than the clock that was 5 feet behind you, you would be pulled toward the clock that was running slower.
I understand that, Eric.
Okay.
I understand quite well. In fact, what my big question comes down to is, how do you actually create a system in which we can observe this experimentally by modifying these parameters? Because normally these are things that are totally untouchable to us humans. We want to.
I'm telling you. So I'm telling you. So now take that example and now look at a satellite orbiting the Earth, and at a constant altitude. It needs to, and assume it's a circular orbit, it needs to have an exact orbital velocity so that it stays in a circular orbit, or else it's going to be sucked into the Earth, or the orbit's going to be parabolic, and it'll escape the gravitational field. So it has to have this specific velocity. So there's a way to derive the velocity that object needs to stay in orbit and correlate it with the time dilation that object is feeling as a result of the gravitational field that the Earth is producing. And when you do that, you can then remove the Earth and say the Earth is no longer creating the gravitational field. There's actually an electromagnetic effect going on that's creating that time dilation. Right? You don't need the mass. The mass is a proxy for matter, and so you need to figure out how much time dilation do you need to induce artificially in order to cause an object to accelerate. And you can figure that out just by looking at the gravitational time dilation and how fast you have to orbit around the Earth to get that balance of forces. So then, when you map that to the gyroscope, you just think of the rim of the gyroscope as the orbital velocity that's required to keep that satellite in orbit, right? And then you just imagine that the radius to the center of the rod is the altitude to the Earth, and then there's another reason, but then you have to rotate the whole mechanism. So you can actually figure this all out. It's not terribly difficult. It's just that I can't. If I told you how to do it, there'd be a lot of people that'd be mad at me. And it's not because it's classified or anything like that. It's just that a lot of people worked hard on it, and in the end, it did not lift itself off the ground. But like I said, in other configurations that weren't vertical, you could see the effect, right?
That's significant. I've seen a few very interesting videos as well, which I'm not going to bother trying to link right now, which seem to demonstrate the effect that you're talking about, and it's interesting to link them together now with what you're saying.
Yeah, I'm saying anybody that wants to try to work on it, try to think of it in terms of time dilation. And hey, maybe there's a better way to think about it, but that's the way that well, actually the group I was in, they were not thinking about it in terms of time dilation. And I was the one that told them that that we should be thinking about it in those terms. But I believe those are the correct terms to think about it. Is how can you create how can you artificially induce a time dilation gradient to cause acceleration in the same way that the Earth causes acceleration through its gravitational time dilation. So you can go to Wikipedia and you can look up the formula for gravitational time dilation. And it's very simple. And if you just think about it, you know, it might only take a month, and you probably figure it out.
So you're talking,
but in terms of propulsion, I mean, if your goal is to really get something moving and going without question, and using it to launch stuff into space, I know that the gyroscopic mechanism has potential. I don't think it's going to be lifting payloads into space, but I do think it could make for some really cool children's toys, right? Where, you might have like a little, like a skateboard that can hover a little bit or something like that, right? Things of a much smaller magnitude.
I mean, right now we're basically fine with that. We're just simply trying to prove some principle out and have it in a demonstrable fashion where we can at least prove some of these concepts that, we want to point out the issues in the heavy side.
Well, then
and we want to show that there's other things to learn.
And if you want to do that, then and this has nothing to do with Richard's company. This is just me saying that if you want to try that, my suggestion would be you just get a rod, a flat rod, sturdy rod, and you put a disc on one end and a disc on the other end, right? So that's perpendicular to the rod, so that the disc can spin on the axis on both sides, and you have it spinning in one direction on one side and the other one on the other side at the same speed. And then you rotate that whole mechanism around like a helicopter blade. But before you do that, you need to do these calculations with the time dilation, gravitational time dilation.
I tried that, Eric. I tried that at 10,000 RPMs, that exact experiment that you just described, and I had them mounted at exactly 90 degrees. Mm-hmm. Maybe it was just my test setup where the noise floor was too high, and I didn't rotate them around at a particularly high RPM, only about 100.
No, but it's not 90, right? Well, wait. So you had a flat rod, and then on the end
I had two separate synchronized motors instead of using a connecting rod.
Okay.
But they were both mounted on a solid piece of square stock, and then in the very center of that square stock was a bearing that could freely rotate, and I would forcibly rotate the entire mechanism with both gyros mounted to the very end of that thing. And I ended up getting a lot of vibrations on my scale, but I wasn't able to observe any reasonable force in 100 RPMs.
So just so I can visualize, so you've seen Lathweil's his I can't even pronounce his name right.
He lifted the gyro up over his head when he took the entire shaft and he swung it around his whole body. Right.
So what you need is you need to have that shaft parallel to the ground with the disc perpendicular to the ground, right? And then you need to put another disc on the other side of that rod, perpendicular to the ground. You need to spin the discs in opposite directions with respect to each other. And then you need to rotate the entire rod in a helicopter fashion.
That's exactly what we did, but I just realized, and you're talking about it, exactly where my measurement problem was. Just ironically, in talking to you right now, I just realized where my measurement problem was, and I think that we could probably replicate that now, especially because Falcon Space has new gyroscopes coming in, and we'll be able to easily put this experiment into test. We should be able to rotate.
But you won't. But it won't work unless you calculate the proper. You need to have the proper angular velocities for the two discs and the proper rotational velocity and the proper diameter for the discs, so that the hypotenuse from the top of one disc to the center of the rod, that's the hypotenuse of the triangle, that length comes into play in the formula that you're going to have to derive, which you will derive from studying the like I said, the velocity at which a satellite has to orbit to stay in orbit and fight off the time dilation that's pulling it downward, right?
So if the RPM was too fast on these gyros, it wouldn't work, or if their spacing was too far apart, it wouldn't work. We have to line these.
Yes, yes, everything counts. The diameter of the discs has to be right. The length of the rod has to be right. The disc, there has to be an exact center of mass in the rod, right? So the discs are exactly the same space apart, radius wise. The angular velocity of the discs, the rotational RPMs matters, and then the RPM of the entire rod going, like in a helicopter,
right,
that way, with the discs on the side spinning themselves, right, in their own direction, orthogonally. All of those measurements and all of those rotational velocities, angular velocities, have to be correct and match the time dilation that the satellites are overcoming by their tangential velocity, so that they don't get sucked into the time dilation gradients of Earth, right? So by them moving at a velocity, they're actually causing a reverse. They're actually counteracting the time dilation that's imposed upon them.
Maybe
so in effect, they're causing time dilation, right? Without length contraction. Without length contraction. So it's not special relativistic time dilation. It's a different kind of time dilation. And it maps right down into this geometry that I told you about. And you actually already did it. So all you need to do is you just need to figure out the right dimensions and the right angular speeds. And then what you'll find is that you'll hit the point where you match gravity, and then you need to adjust the rotational parameters so that you can actually create more than 9.8 newtons of force upward, and then you can then hover. But like I said,
Eric,
don't fight gravity. Just put it on a train track.
How about we put it on a pendulum system with a weight on the opposite side and just hang that, and then if there's a tiny bit of weight loss, we can see it without any shaking scales.
I mean, I don't know how you're going to do that, because you have to have the disc rotating and the whole rod rotating. I mean, I'm more of a physicist and an engineer, so I can't picture what you're saying. But
well, how about this? If we can get it to spin in one direction, then we'll build another device and put it on the other side of equal weight. See if we get linear motion.
Yes. I mean, experimentally, I think you would probably know better than me what to do. I would just recommend don't try to lift it off the ground. Just try to have it push itself forward on a track or equivalent, right? Try to have it displace itself in a way that's unambiguous.
May I ask you a question, Eric? Very important one. If we were to take these two gyroscopes that are mounted on this shaft, is the length of the actual rod that rotates around like a helicopter blade directly correlated to the RPMs of the gyroscopes,
Yes.
or do these figured out?
Yes.
Okay, so, and
But
I would ask this other question: does changing the RPMs of the gyroscope actually change perhaps the necessary length of the rod, or is that a factor that you have to get right, and there is only one correct solution for it?
Well, actually, it is. There's two different equations, so they're coupled. What matters most is the hypotenuse, right? Well, that's not what matters most, but so if you start the measurement at the top of the disc, and then you go straight down to the center of the rod, and you just in a straight line, then you have a triangle, right? You have the rod is the base, the disc is the height, and then the hypotenuse is that moment arm down back to the center of the rod, right? So it's that hypotenuse length that comes into play in the equations. So it's not the rod length, it's the rod length plus the diameter of the disc, the combination of those two that matters.
So if we change the RPM and kept the disc at a fixed length, and we let's say we had a disc of let's say we had
I see what you're saying. You're saying can you just build any device and run it through just every permutation of angular velocities?
You got it. Exactly what I'm saying. Thank you, Eric. Is exactly what I'm asking.
I don't, because there's two equations that are coupled, I don't think you can do that, but you can certainly try, but it might take you forever to figure it out, because you're gonna have to like bump up the velocity of the angular velocity of the disc while you're also changing the rotational velocity of the rod and the RPMs of the rod. And it's just like you can do that all continuously, but you have to stop and see if you see an effect, and then you're gonna have to do that for every permutation, and there's an infinite number of those. So
yeah, I figure we just pick a fixed RPM and we pick a fixed rod distance, and then we can either increase the helicopter blade-like rotation of the entire system, or we can pick a fixed helicopter blade-like rotation of the system, pick a fixed angular rod length, and change as a variable the RPM of the gyros, or we can keep the gyro RPM and the rotation speed constant. We could change the fixed length of the rod. I mean, we have three different variables.
You can try doing that. I think that there are a lot of, but see, you have to also wait to see if you get the effect. The effect is pretty immediate, but you can't just cycle through in a continuous fashion. You'll have to do it in steps, and then you might jump over the velocity that you actually need. It's worth a try, but you might waste a lot of time trying it unless you write a software program to do it, and then just let the thing run and for days and days until you finally the software program sends you notification saying, yeah, we noticed some the weight changed on the scale, right? You can try that, but
actually we are setting up to software automate our test for Elzaphan, because we believe that the parameters are so precise and such a narrow band that if we hit it, we may very well visually miss it. So we're going to try to get a computer to look for that data for us, and figure if we build that system, we could potentially brute force this whole gyroscope thing too. That's a possibility.
I just want to go for it, but it's permutation hell, trust me. And if you have a software program that can do it all automatically and you let it run for days and months and then you finally get a result, that's great. But if you're going to do it by hand, it's going to take too much time. And if you have any kind of if you have any scientists that work with you, they could probably figure out the equations. And so there's two equations, and they're coupled. And that's why I don't know if the permutation thing will work, because I don't know if running through those permutations will actually be equivalent to solving the coupled equations. You see what I'm saying?
Yeah, I see exactly what you're saying. It's extremely good advice, and I'm sorry to ask so many questions to kind of clarify what you're saying. I wanted to get a full picture of the information you're presenting, and I think you've given us a very good one now. So we have a direction to work with. Really, we have to do the math. We have to figure it out ahead of time and get those parameters exact. And luckily, in 2020, we have the ability to spin something at an exact RPM and know what it is. So that's a factor that we can kind of eliminate out of our difficulties.
That's what I wanted to ask you guys. We need to get a RPM meter. Any recommendations?
All you really need to do is put like a piece of reflective tape on the disc and shine a laser on it, and you probably have a laser there, and just check for the reflected pulse back.
Yeah, just buy a cheap $45 laser tachometer from eBay, and I think we'll be good for just checking RPMs. We're only verifying, right? If we want a live monitor, we can get a tachometer panel meter.
Also remember, you want as much weight as you can at the rim, right? You don't want to have a solid disc. You want to try to maximize the weight so it's at the rim of the disc. And that's where the coupled equation comes in, right? So it's it's there's the velocity, there's the moment arm length.
How's this one?
And then there's the distribution of matter on the disk, and that's where the second coupled equation comes in.
Jeremiah, how's this one? Oh, we can't see it.
Well, I can kind of see it. You just got you have to I think maybe hold it a little closer, because right now the background light is saturating the screen. There you go. There you go. Take a look. You'll use a tool forever if you get one of these infrared thermometers. Get a Raytech or a Fluke. Do not get that. There's a little bit better technology in the Flukes, and Fluke bought Raytech actually, and they just have a better sampling rate than the others. You don't want to wait half a second or 1 second to get every single measurement. They're worth it. Like
I just say with sorry.
Oh, I'm sorry. You're looking at RPM meters. I thought you were looking at that. Looks like an infrared gun.
It's a laser tachometer.
Oh, sorry. My bad. Yeah, any laser tachometer will be just fine. I mean, frequency counters are fairly accurate. Crystals are going to be good enough.
But I'll tell you with Tim, just real quick, Tim Ventura. I really appreciate that he wants to keep the email list focused on engineering, which is exactly what he should be doing. But I have to caution you. You really need to understand the science as much as possible, because you will waste a lot of time just trying to brute force things. And thankfully, the gyroscope stuff really isn't that hard to figure out mathematically, because it's all there. The solar system's telling you how to do it. So so that would be my advice: is either yourself, or if you know a smart high school kid, or a physicist in college, see if they can figure out the equations.
Well, and actually, Jeremiah and Mark as well have been doing a lot of the equation work. I think the reason they had started with kind of an engineering focus is, once you open the door for kind of theory only, and I'm sure you've seen this as well, right? You have no idea what's going to walk in, so to speak. And it becomes very difficult when it's theory only, and that's why people who are focused on the physics like yourself have very small lists, because you've got people coming in bringing all sorts of I think this theory, I think that theory, and so by focusing it in on the engineering part, what they've tried to do was keep it focused on stuff that's testable, where you can get a yay or nay.
I've done a lot of engineering.
Oh, sorry, your mic cut out.
Oh. I appreciate both approaches, but I would just say the full brute force approach is just a real long shot, no matter what you're doing, whether it's a gyroscope or trying to get Albuquerque stuff to work, whatever. I mean, that's
Well,
just really.
yeah, and from my perspective, I mean, me personally, and again, they kind of got me engaged in this. My hope is, and I realized this quite a while ago, it's how can I best be of service to the community and to other people? And I'm like, well, what I can help do is document and archive and get the word out, right? And so that's really my primary focus. I don't have nearly the understanding of this that you guys do. My physics is like 12 years rusty, and so really my focus is I've been blessed to meet some of the most brilliant people in this area. And so, can I just help them, help them reach just a few more people? If I'm able to do that, for me, that's what I consider a success. So.
No, I think you're doing a great job. Yeah, I'm very honored to have been added to the list. There's, there's 110
well,
people.
Thank you for joining us. I mean,
smart. So.
Yeah, I really want to thank you, Eric, for taking the time to tell us about what you know. I know that there's things you can't talk about, but those equations exist, and we can certainly find somebody who can do the complicated mathematics and help figure that out. We do have a few people on the team who have a mathematical and academic background, which hopefully we can get them on.
It's not that complicated, and also, I'd be more than happy to tell you everything, because it's not anything that's classified, and it's not even an NDA issue. It's just that people that I respect and who respect me would be really mad if I talked about how to do it.
Yeah, just on a personal level, maybe off air. I mean, maybe outside the public genre, we can talk about this, because honestly, I think Mark Sokol and I both have the same sort of vision in mind. That is, we want to understand it. We're not necessarily, it doesn't have to be disclosed every single piece. We want to disclose as much as we can, and we want to share with the public what we can. But if there's something else that we can learn about to help us understand the physics better, and that can help move us forward into other topics that we can share, that we can talk about, we're very interested in learning everything we can.
Yeah, I mean, I told you probably almost everything I could tell you, but what I could also do is, once you start doing it and getting the experiments going, you can always email me and say, we're seeing this happen, but it looks promising, but something's wrong. And I could, give you my thoughts on it.
You can expect an email from us, Eric.
Okay. Yeah, that's fine. That's fine. But I just don't think it's going to be it's not a viable launch platform. It's not.
That's perfectly all right. Microsat.
And the reason for that comes out of the equation. So you can sort of see that you're going to be limited in the amount of acceleration, the amount of newtons of force you can generate, because it's a mechanical system, right? And so, but it's very interesting if you can get something moving horizontally along a track without stopping, for 30 seconds. I mean, right there, you'd probably win a Nobel Prize, because you had proved propellant-less propulsion works. And you could also make a lot of money selling children's toys, right? I mean, kids would just love that kind of thing. But I don't know that you'll take over the launch market.
We're not necessarily trying to take over the launch market. We just really want to understand, hey, if there's a toy out there that we can produce in mass that teaches the youth about the existence of these things, that there's more to the physics than is simply understood by the textbook, and that we can actually move forward with our education as a species, then we're all for that, 100%.
Yeah, well, the gyroscope, I'll just tell you, it does work, and there's many people think it doesn't work. People that I had worked with in this project think that it doesn't work, but later on in the project, it was working. It just wasn't working. It wasn't working well enough to be useful. And we could have gotten it working better. We lost. We had no money left, and we did get it moving, but it convinced me, and it convinced a lot of people, but it wouldn't pass the public sniff test. People would just be saying, no, it's not quite doing what you're saying it's doing. But I think if you guys really worked on it, you could probably get it going. But it takes time, it takes money, and you have to decide what you want to put your resources into. So, but listen, I gotta go. I had my eye removed a while back, and I get just a lot of eye pain at this time of night, and I'm really dehydrated, so I need to take off now. And
thank you so much again.
So much. That was very helpful.
Thank you.
oh, thank you. No, I appreciate it.